Yeah. Okay, I think we can start now. All right, let's get started. Okay, good morning, everyone, and welcome to Kia's Quantum Many-Body Seminar Series. It is my great pleasure to introduce today's speaker, Professor Masafumi Udagawa. He's a faculty member of Gakushuin University in Japan. He received his PhD from University of Tokyo under the supervision of Professor Masao Ogata. After his PhD, he was a research associate in University of Tokyo. This position is like an assistant professor, right?
Yes, now.
Yeah, right. And also he was a visiting researcher in Max Planck Institute, Dresden, for several years. And he joined Gakushuin University as a faculty member from 2015. He has been working on various topics of condensed matter physics, superconductivity, quantum lattice systems, quantum spin ice, and Kitaev spin liquid, some of his research areas. Today, he's going to tell us his recent work, local detection of Majorana zero mode in Kitaev's chiral spin liquid. Let's welcome Masafumi Udagawa.
Yeah. Thank you very much for a very nice, kind introduction. And I'd like to thank the organizers to giving an opportunity to talk in this Kia's Quantum Many-Body Seminar Series. My name is Masafumi Udagawa from Gakushuin University in Japan. And this picture is one of the main buildings in our university. So I hope you can feel a bit of atmosphere in our campus online, okay? So, today I'll talk about our recent study on local detection of Majorana zero modes in Kitaev's chiral spin liquid. This presentation is a collection of the works listed here, which are in collaboration with Roderick Messner in Max Planck Institute in Dresden, and Shintaro Takayoshi in Kona University, and Takashi Oka in ISSP in Japan. Okay, the outline of my talk is here. The first part is just to give a brief overview in this field. I will give a brief introduction to Kitaev spin liquid with a special emphasis on its chiral spin liquid phase, where two prominent phenomena are expected. The half-integer quantization of thermal hole conductivity and the appearance of Majorana zero modes. And the second part of this talk is about our work on the dynamics of Kitaev spin liquid. In this part, we take up the integrable limit of this Kitaev's model and introduce an analytical solution of finite temperature dynamical correlation function, which we developed in our previous works. With this solution, we address the dynamical response of the chiral spin liquid phase of Kitaev spin liquid. And finally, this is my recent work. We consider the possible role of charge degrees of freedom in this system. In Kitaev's system, it's an insulator, so charge may sound a little strange. But we will propose to detect and even manipulate Majorana zero modes by considering the charge response of this system through scanning tunneling spectroscopy. Okay, so let's start with the introduction. Okay, so in this talk, we will consider Kitaev's honeycomb model. I think many of you have already known this model very well, but this model consists of spin 1/2 defined on a honeycomb lattice. And the spins are interacting with each other through the Ising type interaction with bond-dependent anisotropy axis. Spins want to align in X direction along the red-colored bonds. Meanwhile, they want to align in Y and D directions along the green and blue bonds, respectively. So if all the spins are aligned in X directions, they satisfy the red bonds, but conflicts arise in blue and green bonds. So as a result of this frustration, simple ordered states cannot effectively lower the energy of the system. And instead, the ground state of this model supports a quantum spin-liquid ground state as described by the exact solution. Okay, so let me summarize the structure of the exact solution briefly. To obtain the exact solution, we need to express spin operators by Majorana operators. And with this rewriting, the model can be mapped to the free Majorana fermions interacting with conserved Z2 fluxes defined on each hexagonal bracket. And since this Z2 flux is a conserved quantity, all the eigenstates are labeled by a set of their values taking plus minus 1. And in this classification, the ground state belongs to a simple sector where all the Z2 fluxes take plus 1. In other words, the hexagons carrying Z2 flux minus 1 can be regarded as an excitation, and we call it vison. So in this system, we have two species of excitations. One is Majorana fermion described by this C operator, and the other is this vison. Okay, so this is a concise summary of the properties of Kitaev spin liquid at low energy. And then what signature can we expect in this quantum spin liquid state? Okay, the most remarkable property of Kitaev spin liquid is the appearance of chiral spin liquid state, which is stabilized by applying magnetic field, as pointed out by Kitaev himself in his original paper. For this chiral spin liquid phase, we have two important predictions. One is the half-integer quantization of thermal Hall conductivity, and another is the appearance of Majorana zero mode. In fact, the first prediction of half-integer quantization may have already come true in Kitaev's candidate material, alpha-arseninium trichloride. The low temperature phase of alpha-arseninium trichloride is the ordered magnet with so-called zigzag pattern. However, if you apply sufficiently large magnetic field to destroy the magnetic order, the system becomes non-magnetic, and the half-integer quantization of thermal Hall conductivity was reported by Professor Matsuda's group in this region. So it implies the chiral spin liquid state is stabilized in this field-induced non-magnetic region. Okay, still, the interpretation of this experiment is not completely settled, and even competing experiments are coming on. But one promising and perhaps most exciting interpretation of this experiment is the formation of chiral spin liquid phase. So given the half-integer quantization is already observed, the next issue must be the detection of Majorana zero modes. Indeed, these two phenomena are two faces of the same coin. So in the chiral spin liquid phase, the excitation vison accompanies Majorana zero mode, and it is expected to behave as non-Abelian Ising anyon. In this light, its detection is not only a task of condensed matter physics, but is crucially important in broader context involving the research area of topological quantum computation. Then what is the current experimental status regarding the detection of Majorana zero mode? Yeah, indeed, plenty of efforts have already been made to detect the Majorana zero modes. These are the collection of the spectroscopic experiments conducted for alpha-arseninium trichloride in a magnetic field, ranging from Raman spectroscopy, inelastic neutron scattering, and electron spin resonance, and terahertz spectroscopy. All these experiments commonly observe multiple spectral lines, and it's a complicated reconstruction at the breakdown of magnetic order. So if the chiral spin liquid is realized close to the phase boundary, these spectral lines should contain the information on Majorana excitations as a result of the recombination of excitations. However, regarding this point, we could not reach a consensus yet. For the first two works mentioned above, cited above, based on Raman and inelastic neutron scatterings, they attribute one of the resonant peaks to the possible existence of Majorana zero modes. However, the other two works do not. One major reason for this discrepancy may be the lack of theory connecting the spectroscopic experiments and the presence of Majorana zero modes. Okay, so for this reason,
can I ask a question?
Anytime. Yeah.
Can you go back to the previous slide?
Okay.
This one. Yeah. So you mentioned that there is a inconsistency between different experiments. Is it because of sample?
I don't think so. It's just a problem of interpretation. Some experimentalists, like to insist that they found Majorana zero modes, but yes, other people are more reserved at that moment, probably. I don't know exactly if they are working on the same or similar samples, but yes, that's definitely a point we have to check.
Okay, thank you.
Thanks. Okay, please ask me questions anytime. Good. Okay, so given these motivations, we first try to address the dynamics of Kitaev spin liquid and try to find a clear signature of Majorana zero mode in the dynamical response of Kitaev spin liquid. Okay, to address the dynamics, we especially focus on the low temperature region where a small but finite density of visons are summary excited, accompanying the Majorana zero modes and interact with each other. So in this region, we can expect a dynamical response involving the effect of Majorana zero modes, and it is relatively easier to extract the information of them from the spectroscopic features. And specifically, as a theoretical model to describe the chiral spin liquid state, we consider the ferromagnetic isotropic Kitaev's model, supplemented by 3 spin interactions mimicking the effect of magnetic field. And Kitaev used perturbation theory to derive this Hamiltonian, assuming this kappa, the coefficient kappa, is small. But we'd rather regard this coefficient as a phenomenological parameter to describe the excitation gap of this effective theory. And in fact, it was pointed out that, for example, non-integrable interactions enhance the magnitude of this coefficient. And in the experiment of field angle dependence of specific heat, where I think Hewson and Jung made a theoretical contribution, the magnitude of Majorana gap is estimated to be rather large, of the order of 10 Kelvin. So we don't necessarily need to assume that this parameter is so small. Okay, so in Majorana representation, sorry, the Hamiltonian is rewritten as Majorana originated fermions interacting with these fluxes or visons. We use classical Monte Carlo scheme by sampling the conserved Z2 fluxes and address the finite temperature properties of this system. And okay,
question.
Sorry. Yes, please.
Yeah. So, so in this Monte Carlo simulations, are you using Jordan-Wigner?
No. I use the Jordan-Wigner formulation was used by Motome's group, but I use this Kitaev's representation.
The original one.
The original one. Yeah. The advantage is you can do many things like changing boundary conditions or introducing some complicated defects or vacancies. And I think the result is the same. But at the cost of flexibility, we need to be careful to a few points, like we have to fix fermion parity or some technical points. But yes, results are equivalent. Yeah.
One more question. Then how do you reproduce the physical Hilbert space?
Yes, that's the point. So mostly it is accounted for by fixing G2 fluxes. This is only the physical conserved quantities. But the minor point is you need to fix fermion parity. Yes, that's a little bit technical point, but you need to prepare sort of partition function in the different parity sector, and by making a summation over them, we can pick up desirable fermion parity. And if you make this prescription, you can obtain perfectly exact solution.
Excuse me, may I ask one question? So you're talking about fermion parity. So are we talking about like periodic, doubly periodic boundary condition?
Yes.
Are we doing this calculation on torus?
Yes. Usually working on that torus with periodic boundary conditions in two directions. Okay, good. So let me proceed a little bit more. So, so with this formulation, we calculate the spin correlation function from which we can extract dynamical magnetic structure factor relevant to inelastic neutron scattering and other interesting observable quantities. Okay, one important property of Kitaev's model is that the spin correlation function is extremely short-ranged. This property comes from the conserved nature of G2 fluxes. So for example, if you apply the Z component of spin at this site I, then a pair of G2 fluxes change their values on the both sides of the Z bond, extending this from this site I. Or maybe you can interpret this result as a shift of vison over the bond. This is a rule. So for the spin correlation to be non-vanishing, we need to come back to the initial configuration after the operation of second spin operator. So this is why the correlation survives at most up to nearest neighbors. And in addition to this non-trivial constraint imposed by G2 fluxes, we are also left with the task to evaluate this fermionic propagator. Since the Hamiltonian is Majorana quadratic, it may not seem a difficult task at first sight. However, due to the change of flux configuration, so it is accounted for without dash and with dash. The intermediate state is described by different quadratic Hamiltonian from the initial state. This brings about a difficulty. But a few years ago, we tried to overcome this difficulty and succeeded in deriving the following analytical expression of the dynamical spin correlation function. This expression still seems complicated and even contains the summation of G2 fluxes. So we need numerics to evaluate this quantity. But nevertheless, this expression is useful since it allows direct access to real-time and real frequency representation of correlation function without analytical continuation. So our solution gives an effective approach to the equilibrium dynamics of Kitaev's model, and beyond that, as a potential application to time-dependent non-equilibrium problems also. And yes, this is the fermion parity. And yeah, answering the previous questions, we need to properly make a summation of the ordinary partition function and contribution from the twisted partition function. And this is accounted for here. Okay. Good. Then, as a simple demonstration, okay.
I have a question.
Yes, of course.
The
Yeah.
previous slide. So the
yes.
yeah. So in the line of this Hamiltonian.
This.
Yes. On the right hand side equation, there's k and k prime index.
This.
Right.
Okay.
That's the momentum.
Not momentum. Sorry.
It's not momentum.
It's just the site in the
site index. I see. I see.
And summation is assumed in first two.
I see. Okay. And then this flux configuration is there is this additional degree of freedom, so-called this gauge degree of freedom. So and you think this expression. So I think this dynamical response or dynamic correlation function must be a gauge invariant, basically. So
yes, of course, yeah.
Okay. And then is there a way to see this gauge invariance? So since you said it's exact, there is no. So I presume this expression is a gauge invariant.
Yes, yes, it's gauge invariant, and how to. Your question is how to make it clear.
Is there my question is looks like A is clearly gauge dependent degree of freedom.
Okay, yeah.
And then the question is that the final result must be then.
Yeah, that's a good point. And maybe how can I answer your question? But okay, gauge. Okay, yes, I can answer your question probably. At least, okay, so look at this determinant. And gauge transformation is described by unitary transformation by changing sign for the matrix components that connect one site where you impose gauge transformation.
Right.
And this unitary, in terms of this unitary transformation, this determinant is obviously unchanged because you can set U and Udaga here, and you can exclude that matrix inside the determinant. Okay. Then the next question is about this part. Probably same thing happens.
I believe you.
Is it okay?
Okay. I mean, this expression is very nice. I mean, it's an analytic expression basically, and right. Yeah. And okay. Yeah. Maybe we can discuss later.
Yes. Yeah. I'm happy to.
Yeah.
Okay.
Actually, I have a question. It's about this analytic expression. So so this analytic expression is valid as long as we I mean the model is exactly solvable, right?
Yes. Yeah. Exactly. As long as it is described by Majorana quadratic with some classical fields.
I see. Oh, this is very useful.
Thanks a lot. Yes, indeed. Yeah, that's what I want to demonstrate in this slide. The most how to say the good point about this expression is you can calculate correlation function, dynamical correlation function in terms of time variable, even at finite temperatures. This is quite exceptional in quantum many-body systems and for more than 2 dimensions. Even in integrable model, like like spin 1/2 Heisenberg chain, it is not easy to access the time-dependent dynamical correlation function even at finite temperature. But in Kitaev's model, it is possible with this solution. So yeah, beyond the result I'm introducing in this seminar, I think this technique is useful to much broader problems. That's what I want to strongly insist.
Okay.
Okay, so given this introduction of model and the method, let's move to results. Some of you may have heard about this result already in previous workshops, but nevertheless, I want to. Okay, so this is the first result, and I'll start with the thermodynamic properties of this system. The red point is a plot of specific heat, and the blue point is a flux average. So it means if this blue line reaches 1, then there is no vison in this system. So at low temperature, there is no vison excited anymore. And we also show the specific heat at 0 magnetic field or 0 kappa in the previous slide with this black points as a reference. And it's shifted due to the effect of that magnetic field. So apparently, we have two energy scales in this system associated with vison and fermionic excitations. And it is reflected in the double peak structure of the specific heat. The high temperature peak corresponds to the energy scale of Majorana originated fermions, while the low temperature peak is related to visons, where vison density quickly decreases from the low temperature side. Okay, then let's look at the.
One more question.
Of course. Thanks. Yeah.
Can you go back to the previous slide?
Yes.
So the gray points correspond to the 0 magnetic field case, right?
Yes.
And the red points for non-zero magnetic field case.
Yes.
Then I see there is a slight shift in the first peak. So the first peak corresponds to the energy, the size of vison gap, right?
Yes.
This data suggests that there is some renormalization of the vison gap.
Yes. By the magnetic field. Yes.
Magnetic field. I see. Okay. So can you okay, maybe not possible. Is it possible to derive analytical expression for the vison gap?
But
I guess it's not a simple problem.
Yeah. Okay, how to say? But if from the numerical data, you can make a fitting and obtain some simple analytical formula. And another thing is, okay, so suppose you excite a pair of visons, make it very distant, away from each other. Then in the chiral spin decay phase, each vison is dressed by a Majorana zero mode, and that makes the shift of excitation energy. So maybe based on this physical picture, you can derive a nice analytical formula. But I've never thought about that.
Oh, okay. Thank you.
Yeah, you must be interested in this. Yeah, that kind of problem.
Yes.
Okay. Good. Then let me proceed a little more. Okay, so this is the dynamical structure factor obtained from spin correlation function. And this is a result at relatively high temperature, just below the fermion peak of specific heat. The spectrum is still broad, and only some intensity accumulate around zero energy. But as decreasing temperature to approach the low temperature vison peak of specific heat, the structure factor develops a peak, and we can even observe a multiplet of peaks below the main peak. And as decreasing further, the temperature further, we observe a sharp resonant peak evolving at this a little bit higher energy compared with the multiplet I showed you. Okay, so for all the temperature range, the momentum dependence is very small in this model. Then let's focus on this zero momentum sector, gamma point. Then if we focus on this gamma point, at high temperatures, this green line, the spectrum has only a broad peak around zero energy. Then as decreasing temperature, this broad peak first turns to decrease, and a sharp, then as decreasing the temperature further, a sharp resonant peak appears, and the most okay, so then it evolves very quickly. And the most non-trivial place is in this transient temperature, 0.025, shown by this orange line, where we can find the multiplet of resonant peaks. Okay, so this transient region corresponds to the low temperature peak of specific heat, where a small density of thermally excited visons exist, accompanying Majorana zero modes and interact with each other. And this is a region where we can expect a response characteristic of the Majorana zero modes present in the system. So the question is, how can we understand the origin of these resonant peaks obtained in this region? Okay, so let's look at this spectrum in this transient region with temperature variation in a smaller width. Then we have 3 peaks in this low energy region. And firstly, regarding this lowest energy peak, what's the origin? That's a question. And to understand that, please remember that if you excite a spin, then it makes a shift of one vison by one lattice space over the bond. Then if visons are sufficiently apart, then this process makes almost no substantial energy change. And consequently, we observe this zero energy broad peak. And since this peak assumes the presence of thermally excited visons in the initial state, as temperature lowers, it gradually decreases. Okay, then next, for this highest energy peak, we can attribute it to the process of vison pair creation from the vacuum. This peak, in contrast to the lower energy peak, evolves into a sharp peak as decreasing temperature because it assumes no vison in the initial state. And finally, the peak in between, this has more subtle origin. To understand the origin of this peak, we note that visons have attractive interaction with each other. Since 2 visons carry 2 Majorana zero modes in total, and they have a fusion channel into one fermion, whose energy is lowered as 2 Majorana zero modes have larger overlap. So to put it another way, suppose a vison pair exists in the first place, then it requires substantial energy to dissociate them. And this process, the dissociation of a pair, corresponds to this intermediate. So, okay, so summarizing, in this transient region, we have 3 peaks associated with vison displacement, vison pair dissociation, and vison pair creation from the low energy sites. This is the main result of this part. Okay. So then, okay, of course, yeah.
So you're describing the interaction between visons entirely in terms of the effect on the Majorana zero mode.
Yes.
But I mean, so I mean, could you explain why we can confidently rule out any possibility that higher energy excitation may actually
yes,
have
yeah,
some
of course.
effect on the interaction?
Of course, they can contribute, but a dominant interaction is mediated by Majorana zero modes. And actually, this green line is not a fitting, but a result of the calculation that estimates the bound energy of 2 Majorana zero modes. Okay, so we more precisely, we calculated the energy of fermionic mode in the initial state, where 2 visons are exactly next to each other, and the fermion energy of this configuration. Then, if you plot the difference of these energies, yeah, it appears here. So it almost coincides with the peak. So that's why we concluded that Majorana zero mode is the main driving force, and the higher energy fermions are not so important for the place of this peak.
Okay, thank you very much.
Yeah, thanks a lot. Okay, so this is the theoretical result of dynamics. But okay, so let me just briefly introduce the connection with experiments. Maybe the result of experiment is a little bit old, but okay. So in Raman scattering experiment, actually they found the growth of the peak in field-induced non-magnetic region here, and they associated the growth of the peak with the pair dissociation process we have just discussed. I have a little bit different opinion, but actually the pair dissociation process is considered to interpret actual experiments. And also, inelastic neutron scattering experiment also found a peak around 3 millielectron volt. This is a little bit complicated, but this is a data for gamma point, and the different lines correspond to different magnetic field. And this gray line is 8 Tesla here in the field-induced non-magnetic region. So it is tempting to associate this peak with pair creation peak I have just discussed. But one major discrepancy with our theory is they found a peak at gamma point, but not M point. At M point, this gray line is very flat. So there is no peak here. So while our result, theoretical result, has only small momentum dependence, so this discrepancy may be resolved by considering the non-Kitaev interactions not included in our model. So non-Kitaev interaction will introduce dynamics to visons, and it may change the momentum space structure considerably, but that's a future work. Okay, so this is the end of the second section. And summarizing so far, the dynamical response sure involves the information of vison and associated Majorana zero mode. However, the connection between theory and experiment is influenced by the factors like non-Kitaev interactions which inevitably exist in realistic materials. So it would be nice if we could come up with more direct method to connect Majorana zero mode with observables. And it is what we want to address in connection with the charge response of Kitaev spin liquid. Okay, to catch the signature of Majorana zero mode, desirably, we want to do something like this simple illustration. If we can set up a sort of potential well that works on Majorana zero mode, you can trap and control it as you like. Okay, but it is easy to say, but very difficult to do, since we have no coupling terms available that connects a single Majorana zero mode and local observables. So this robustness of Majorana zero mode is usually considered as an advantage in terms of protected topological quantum computation. However, for the purpose of manipulation of Majorana zero mode, this robustness confronts us as severe difficulty. So to overcome this problem, we can take two possible routes. One is, rather than catching Majorana itself, try to detect vison, which is a kind of vehicle of Majorana. And vison, since vison is observable, and you can catch it by some method like lattice deformation or some preparing some observable experimental probes. And this is an indirect but sensible strategy. But another route is to use non-local probes. And we try to choose this direction by here. Okay. Okay, specifically to detect Majorana zero mode with non-local probes, we pay attention to the charge degrees of freedom. Why do we want to look at charge? Majorana zero mode does not couple to local observables. And in this light, electron charge is of course a local object, but a Kitaev spin liquid is realized in a good insulator with frozen charge degrees of freedom. In this sense, we can regard electric charge as an external degrees of freedom. So there might be a narrow chance that charge provides a way to locally detect the Majorana zero mode. That's the idea. So timely enough, several groups have recently focused on the role of charge in Kitaev spin liquid for the purpose of carrier doping or for the investigation with scanning tunneling microscopy. And at the same time, several groups try to make a ruthenium trichloride thin film, which is necessary to probe Kitaev sample with STM. Okay, we look at charge degrees of freedom in Kitaev spin liquid through a setting of scanning tunneling microscopy as schematically shown here. Specifically, we put a sheet of Kitaev's material, for example, alpha ruthenium trichloride, on a metallic substrate and try to conduct electric current from STM tip to the substrate through the Kitaev's system. We assume, okay, question? It's okay. Okay, so we assume the sample and substrate in equilibrium with a common chemical potential set close to the upper edge of the lower Hubbard band of Kitaev's MOT insulator, considering the case of hole conduction. Then we apply a voltage bias between the STM tip and the sample and make an electric conduction. Oh, sorry. Okay, the advantage to consider STM is it may give us the information of local excitation energy spectrum, which is usually difficult to obtain in magnetic systems experimentally. And in general theory of STM current, the current is obtained as a convolution of local density of states of tip and a system. So if the density of states of STM tip has a simple structure, for example, constant, the differential conductance of obtained from this formula turns out to be proportional to the local density of states of Kitaev sample. Accordingly, the crucial step of the analysis is to obtain local density of states of Kitaev system associated with charge excitation. Okay, to attack this problem.
Question.
Oh, okay, please.
So can you go to the previous slide?
Yeah.
So here you assume the local density of state of the STM tip is kind of constant, or
yes, yeah, constant.
You don't assume any structure on it, right?
Yes, at least for the energy range we are looking at. Yeah.
So okay, I see.
I don't think it's an essential part. Probably you can first measure the density of states of the tip, and based on that, you can interpret the experiment. So I don't think it's an essential part.
I see. Yeah. Okay. Thank you.
Thanks. Okay, then to obtain the density of states associated with charge excitation, we start with the TJ generalization of Kitaev's model by expressing spin 1/2 operator with its original fermion representation. And to obtain density of states, we introduce a whole Green's function of this model, defined by the operation of removing one electron from Kitaev's Motley insulating state, and like this, and filling it in sometime later. And we consider the vicinity of Motley insulating state. At zeroth approximation, we can assume a heavy mass for the introduced hole and ignore the whole propagation within the sample. Within this treatment, the whole Green's function can be obtained from the operation of creating one static hole in Kitaev's model. And accordingly, by applying the technique to derive a dynamical response function I introduced, the corresponding correlation function can be analytically obtained as this form, like the spin correlation function I showed you. Okay, based on this formula, I'll introduce our results. Okay. Yes, please.
Yeah, here we have two types of T, basically. One
P.
is time.
P, you mean this?
T.
T.
Yes.
Sorry, what do you mean by T?
T there is time, right?
T is time, yes.
Right. In the previous Hamiltonian, the TJ model, T is the
so
right.
Yeah, that's stupid. Yeah, this is transfer integral. Maybe we call it W.
W. Okay. So then, in your then my question is that in your final formula there is no information about W.
Yeah, that I dropped it, assuming that the doped hole is static.
Okay.
Zeroth approximation.
I see. I see.
I think it can be improved in principle, but to catch the qualitative feature, I think it is.
Okay.
Okay. So this is a formulation, and let me move to the results. Okay, so this is the first result of density of state, local density of states of Kitaev's model. And if there is no vison around the STM tip, we can obtain this black line. This corresponds to the configuration without vison. In contrast, this red line corresponds to the case where a single vison is present in the vicinity of the STM tip. And this density of states is observable through the differential conductance through this relation. So if you change voltage bias, the differential conductance changes like this and exhibits two peaks in the presence of visons. And in contrast, there is only a single peak in the absence of vison. So you can clearly see the difference between these two cases. So these contrastive results clearly demonstrate that the charge response is a quite useful quantity to identify the presence of vison. Okay, then what's the origin? Oh, yes,
Sorry, I have many questions.
previous.
Yes. So here, no vison, and then there's a single peak.
Yes.
And then the peak position is basically indicate the this delocalized Majorana fermion with charge gap with Majorana mass gap.
Yes, yeah, but
because
maybe,
of this kappa.
yeah, with kappa, yes, but okay, yes, and but for the interpretation of the position of this peak, maybe it's easier to in terms of the original spin representation. So the peak position corresponds to the energy to cut 3 bonds in this formulation. So we remove one spin here. So the it changes the ground state energy by cutting these 3 interactions connected to this side.
I see. So
and it is estimated by the spin correlation function times interaction times 3.
Then Majorana interpretation may be not that useful for this.
Not, yeah, how to say. Okay, so are you convinced that this energy corresponds to the interaction coupling constant times nearest neighbor spin correlation?
Sounds plausible, yes.
Yeah. Then to calculate, if you are interested in the actual value of spin correlation, then you need Majorana representation to obtain. So maybe if you explain this value from the Majorana language, yes, this is proportional to the nearest neighbor Majorana correlation function.
Okay, maybe I can ask this question. So if I change kappa from 0.1 to 0.2 twice, then what happens to the peak position?
Okay, and you increase the value of kappa.
Right.
Then, okay, in that case, Majorana is more localized in the sense the gap opens. So the nearest neighbor correlation probably increases in that case. Then this peak shifts to higher energy.
Okay.
Because correlation, am I right? But I think correlation increases.
I thought the perfect pure Kitaev model has the shortest correlation length.
Shortest correlation length, yeah. At in the first place, sorry, because correlation length shrinks. It means enhancement of nearest neighbor correlation. But in the integral limit, correlation exists only for the nearest neighbor side. So maybe this intuitive picture is not correct, but yes. Yeah. Yeah.
Interesting. Then, but for a single vison, you have 2 peaks, and the vison energy is associated with which energy scale, like energy difference, or
yeah, that's exactly what I want to talk about.
Okay.
For the origin of these 2 peaks. Okay. So let me go to next slide. So the issue is the origin of different resonant peak structures here. And to understand this, let's look at the change of fermionic energy level structure by removing an electron. So firstly, in the absence of visons, there is of course a finite gap associated with a gap in the chiral spin liquid phase in the excitation spectra. Then we remove an electron here, practically remove one spin or one side. Then you will find one zero mode appears here, which is attributed to unpaired Majorana. So since we have removed one side from the system, there remains odd number of Majoranas left locally. So it means Majoranas cannot pair up completely anymore around this removed site. And as a result, one unpaired Majorana is left in the bulk, and it forms a zero energy state. So it means the injection of a hole practically introduces one Majorana zero mode in this system. Okay, in the presence of, for example, okay, we have talked about the case of no vison, but in the presence of one pair of visons placed distant, placed far away from each other, and it makes a big difference. And there exists one Majorana zero mode attached to each vison, even before injecting a hole. In this case, the hole injection brings about a non-trivial result because the unpaired Majorana introduced by the hole injection close to one of the visons pairs up with the initial zero mode attached to the vison and creates a fermion or a bonding or anti-bonding orbitals if you prefer analogy with maybe chemistry. Then it opens a new channel of electron conduction from STM tip. Namely, when an electron transmits from the STM to the STM tip to the sample, it can excite an fermion in the anti-bonding orbital at the same time. Then this resonant electron tunneling through the vison hole composite can be observed at higher energy peak of the differential conductance. In other words, this double peak structure serves as a signal for the presence of visons accompanying Majorana zero modes. Okay. Okay. Then the double peak structure of differential conductance gives clear evidence for the presence of visons accompanying Majorana zero modes in this scenario. And the difference of the peak energies, the double peak energies, is equal to the bonding energy of Majorana zero modes attached to vison and unpaired Majorana introduced by hole injection. And this is a plot of this energy, and you can find that sorry. This bonding energy roughly scales with fermionic gap in the chiral spin liquid phase. So again, according to the field angle dependence of specific heat in alpha ruthenium fluoride in your work, the gap energy, which is close to the bonding energy, is of the order of 10 Kelvin. Well, so it's within the range of experimental observation. So this observation of double peak structure by STM differential conductance can give a practical and very clear method to detect the presence of vison accompanying Majorana zero mode. Okay, so this is the end of the third part, and maybe do you have questions here? Okay. So to answer your question in the shortly, the energy difference of two peaks corresponds to the bonding energy of introduced unpaired Majorana and the Majorana zero mode initially attached to the vison. That gives this peak energy difference.
I see.
Mhm.
In terms of then what determines the energy scale?
It's mostly the chiral energy gap. I mean, and the chiral energy gap is proportional to kappa, like 3 times square root 3 over 4 times kappa. So yes, it determines the energy scale.
So that's because so for this case, the model itself is exactly solvable.
Yeah.
And we have one additional energy scale kappa on top of this Kitaev interaction.
Yeah,
So
that's
if
a
I
good
have
point.
other interactions.
Yes, yes. So in that case, visons can be mobile. So so you have to solve a problem of a single vison feeding some attractive potential well introduced by the unpaired Majorana. So yeah, it modifies this energy scale, but yeah, qualitatively this result is describes the situation correctly.
Okay. Well, I have one more question. So
of course, yeah.
Can you go back one or two slides? I think here. Okay.
This.
Right. So then, without vison case and then with single vison case, the energy there is an energy shift. So the no vison case, the peak position is different from the
You mean this difference?
Right.
Yeah.
Why? So in your cartoon picture, it seems like they seems to be similar or same.
Yeah, but yeah, it's also simple because a vison weakens the spin correlation, nearest neighbor spin correlation. And this peak is determined by just cutting 3 correlation. So yeah, so that's why the peak shifts to lower energy. Then on top of that, you have a kind of excited channel of electron conduction. And this is given by the energy scale of bonding state.
So maybe I can ask another question. So that,
okay, yeah.
If I have so in general case, this no vison peak must be in the middle of 2 peaks of the single vison. That's the correct statement.
So sorry.
So in general case, so suppose I have a general Kitaev spin liquid. Then I think your suggestion is that for the no vison case, we have a single peak, and I have one vison.
Then
there are 2 peaks. Then what I'm asking is a more general statement. So can I make this type of statement such that for single vison case peak must be in the middle or between these 2 peaks of the single vison? Can I make that statement?
It sounds reasonable because there is a, how to say, clear physical origin. So this shift is connected to the weakening of spin correlation due to the vison. And okay, then this peak might be below this peak, but I think the bonding energy is local and very strong. So it is natural to expect this second peak at the larger energy compared with this single peak. So yes, I think your statement is reasonable.
Okay. Okay. Thanks.
Yeah, in actual experience, maybe we are observing some time series of conductance. So yes, then make a Fourier transformation to obtain something like this. So maybe some mixed peak appears. Yes, probably if you look at that data, yeah, I hope, this structure, yes, can actually be observed there. Okay.
I have one question.
Of course.
So in this calculation, so you assume the same vison configuration, right?
Yes.
You only change the position of the
Yes, I also tried that, and the result was on my paper. And yes, because the Majorana zero mode is localized strongly in this kappa. So if you change the place of vison further away from the hole, top hole, then the these two peaks start to shrink quickly and merges to this single peak if your vison is further enough.
Right. So yeah, in this particular region, so in the case of no vison, so actually there are a pair of visons, but the STM tip position do not see the vison locally, right? Is that right? Or
do not see, you mean the another vison?
So okay, so in the system we have a pair of visons, but the STM tip position is not located around the vison. Is this the case that you consider in the case of no vison, or
no vison, you mean? Yeah, I mean there might be visons in the system distributed at some density, but yes, STM tip is looking at the place where no visons are present nearby.
I see. So in both cases, I mean, so the black data and red data, in both cases, the vison configuration is the same, but the only difference is the location of the STM tip.
In this calculation, sorry, different configurations you assumed. In black data, we introduce no visons.
I see. Entirely flux-free state.
Yeah, flux-free state. But I don't think it doesn't change the result because as you questioned, I checked the dependence of the structure on the relative distance between vison and the hole. Several sites, a few sites are enough to make a convergence to this single peak. So yes, that's in principle introduces difference, but in this calculation, I don't think it's important.
I see. Right. That's quite interesting. Actually, I'm looking at your paper. So the data, the two-peak structure. Initially, there is a two-peak structure.
Yes,
we move away from the vison. Then the peak merges into single.
Yes, is this single peak?
Yeah, the peak. The position of the single peak is pretty same as the single peak position in this slide. Yeah, there is not much difference.
Yes. So I think for large enough kappa, the magnetic field, the state is localized enough. So the convergence is rather fast. But if you consider the gap brace kappa equals 0, then there is a known result in the context of graphene that vacancy makes a localized state, but it's quasi-localized in the sense that it's only the decay is like power law.
I see. Okay. Yeah.
So yeah, in that region, yeah, we have had to be more careful. So yes, as you pointed out, if the visons are distributed at a finite density, then it gives a different result with the completely flux-free case. But for larger kappa, I think it is safer.
Okay. Yeah. Thank you.
Thanks a lot. Okay, so it's already time, but finally, maybe let me briefly introduce our most recent result of how to make a real space manipulation of Majorana zero mode. Only 3 slides for this topic. Okay, so
actually, you can take time. You can take your time. don't get rushed.
Yeah, thank you. Okay. Yes. So we have introduced our theoretical proposal for the local detection of Majorana zero mode, but we want to go a step further and try to manipulate, control Majorana zero mode in real space. So we are looking for that idea, and this is what we want to talk about in this final session. Then, in controlling the position of Majorana, we usually want to preserve its quantum information because we want to use Majorana as a part of qubit for quantum computation. And for this purpose, the previous setup is, the whole injection is not useful anymore, because it lifts the Majorana energy from 0. So it means it disturbs the stored quantum information. So accordingly, we have to consider a slightly different setup of STM, where the chemical potential is set right within the charge gap in this case. Then the magnetic exchange interaction arises between the STM tip and Kitaev sample in this case, and we may be able to use this interaction to attract vison to STM tip. This type of use of exchange interaction was proposed maybe 15 years ago in the name of magnetic exchange force microscopy. Okay, to set up a microscopic model for this situation, we first consider the STM tip as a non-interacting one-dimensional tight binding model and assume an exchange coupling between the STM tip and spin in Kitaev sample processed to the tip. Then, considering only the low energy degrees of freedom, the exchange interaction couples to the position of vison. Namely, if the X component of exchange interaction is considered in this Hamiltonian, it shifts the vison position over the X bond, this red colored bonds, to shift here. So we have this state. And if the Y component of the exchange interaction is applied, then this shifted vison shifts to this place. So the state 1 appears from state 3. So a vison shifts over the Y colored bond. Okay. Then all things considered, these three vison configurations are connected by this exchange interaction. And this problem can be mapped to a spin 1 impurity condor problem by regarding a proper linear combination of these three vison positions as spin 1, 0, and -1. And for example, in the strong coupling limit, this problem can be analytically solved. And the superposition of these three vison configurations gives the energetically most stable state. And okay, we further solve this effective condor problem numerically by density matrix renormalization group technique and evaluate the attractive energy between the STM tip and the vison by comparing the ground state energy in the odd number of vison sector and even vison number sector. And this result of this calculation is plotted here. So assuming that the energy scale of electron transfer integral in the tip is, for example, 1000 Kelvin. So this stabilization energy quickly decreases if tip system exchange interaction is small, but still the attractive energy in this small exchange interaction region turns out to be of the order of 1 Kelvin in this region. So it is not very large, but it implies the possibility that we can control vison in real space by using STM tip as a sort of tweezers. So this is the rough idea. Right. Okay, and I think this result will be will appear in archive maybe in short time. Okay, so this is what we want to discuss in this seminar. And let me summarize my talk. So we talked about three topics: dynamics of Kitaev model, detection of Majorana, and briefly about the manipulation of Majorana zero mode. So firstly, we introduced the exact solution of dynamical correlation function of Kitaev spin liquid and demonstrate it through the dynamical response of chiral spin liquid phase. And the exact solution of dynamical correlation function enables us to analyze the dynamics of this model in real-time domain at finite temperatures. And I think this technology can be applied to much broader problems, including both equilibrium and non-equilibrium dynamics. So if you have some nice idea about a new problem, I really welcome you. Yes. Okay, and in the second section, we show that charge injection by STM can induce a non-local action in Kitaev spin liquid, and it makes it possible to detect the position of Majorana zero mode. And finally, we propose a way to control vison in a real space by using STM tip as tweezers. Okay, so this is everything I want to talk about in this talk. Thank you very much for inviting me, and thank you very much for listening. Thanks.
Oh, it was very nice talk.
Thanks a lot.
Thank you. It's time for questions. If you have any question, just please unmute yourself and speak.
Okay, thank you very much for the whole talk. And I have a question about the last part. So you were talking about how we can move around the
Yes.
vison using the STM tip.
Yes.
But I guess one question that comes out here is like, how can you move them around without exciting the fermionic state by the pair of Majorana zero mode?
Yes. Yeah,
I guess one question we can have is like, how that, I mean, like what range of kappa we should explore to, you know,
Yes, to
Yeah,
answer
because
your question,
two things. Yeah, exactly right. Yeah.
your two questions are, I think, connected with each other. My answer is the larger the kappa is, the better. So because in order to move the place of vison with keeping quantum information, we, of course, extra fermionic excitation is we want that. We don't want that. So we need to change the position adiabatically. And at this moment, we are relying on the existence of energy gap to the higher fermionic bands. So if you, hopefully, if you move the vison slowly enough, then adiabaticity condition is satisfied, then we can avoid the extra excitation of fermionic modes. So that's my answer. So for that purpose, larger kappa is good because it opens the excitation gap to higher fermionic energy.
I see. So I mean, but there's question about the magnitude of the exchange interaction at the STM tip.
Yeah.
So what your point? So I guess I mean, the question is like, you know, if for the adiabaticity with respect to the Majorana zero mode, I mean, I certainly agree with you, but I guess the question is like, how large the exchange coupling to the STM tip should be compared to kappa if you want to move around the vison. Is it like that's okay because it needs to be large mainly compared to Kitaev coupling rather than kappa? Is that would that?
Yeah, as far as the interaction between tip and the system, larger kappa is also favorable for the effective exchange interaction because if kappa is large, I think this works in favor of larger effective interaction between the STM tip and Kitaev spin because the state in Kitaev system is more localized for larger kappa, so it enhances the effective interaction between the tip and the system. But yes, I agree that the energy scale of exchange coupling is a practical problem. And if we can assume like 10 Kelvin, 100 Kelvin, it's very good. But I don't know if it's practical in the actual experimental setup. We have to, yes, discuss with STM experts about that.
Okay, thank you very much.
Yeah, thank you.
I have one question.
Yes.
So is there any ongoing experiment? So actually you suggested we can use STM experiment to detect Majorana zero mode. Is there any ongoing experiment following your suggestion?
At least Professor Matsuda's group succeeded in making a two-dimensional sheet. And also he's working on the STM experiment.
Oh, I see.
Yes. I had a discussion with him a few times, but I don't know how he's designing his experiment.
I see. Okay.
I hope someone yes.
Yeah. Is there any questions?
I have some questions, but I think it'll be better to ask as an off the record
Off the record. Okay.
Maybe after
Uh-huh.
finishing this officially, then maybe I can ask a question.
Okay. So questions? If there is no further questions, let's thank the speaker again.
Thank you very much.
Thank you very much. It was very nice talk. Yeah. This is the end of this seminar. So thank you all for coming to this seminar. Let's see all of you in the next seminar. Thank you.
Yes.
Yeah, thanks a lot.
Yeah, thank you.